Hello there, and welcome back to the Sleep Science. You're standing in the full blaze of daylight, squinting up at a star so bright it paints the inside of your eyelids red. The sun looks steady, dependable, almost boring in its consistency, like that one neighbor who mows the lawn every Saturday at exactly 9 a.m. And yet right now, something in that blinding disk has shifted, not dramatically, not explosively, just a flicker, a tremor in the data, a whisper in the light. You probably won't survive this. Don't panic. I mean long term, in the sense that one day the sun will absolutely engulf the inner planets when it swells into a red giant. So, long-term goals. For now, though, the change is subtle. A slight irregularity in solar radiation measurements, a ripple in magnetic readings. Nothing you'd notice while sipping iced coffee under a patio umbrella. But in a quiet control room filled with glowing monitors and half-finished mugs of tea, someone does notice. So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. And while you're settling in, post your location and local time in the comments. I always love seeing where in the world you're drifting off from tonight. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You imagine yourself inside a solar observatory. The air smells faintly of electronics and dust. Screens line the walls, each displaying the sun in a different wavelength. Visible light, ultraviolet, X-ray. The sun doesn't just shine, it sings in radiation. And today, and one of those notes sounds off. For centuries, humans have watched the sun with a mixture of awe and terror. In 1610, Galileo Galilei famously sketched sunspots after projecting the sun's image through his telescope, careful not to blind himself in the process. His observations help confirm that the sun rotates, because those dark blotches drifted across its surface over days. That was a revolutionary realization. The heavens weren't perfect and unchanging after all. Fast forward to now, and you've got satellites like NASA's Solar Dynamics Observatory staring at the sun 24/7, capturing high-resolution images every few seconds. It's like giving humanity a permanent front-row seat to a thermonuclear concert. And yet, even with all that vigilance, the anomaly almost slips by. It begins as a statistical blip, a fractional increase in high-energy particles, a brief, localized brightening in the corona, the sun's outer atmosphere, which strangely enough is millions of degrees hotter than the surface below it. Yes, the outer layer is hotter than the inner one. If Earth's atmosphere worked that way, mountaintops would melt before beaches did. Physics keeps its sense of humor. You lean closer to the monitor. The brightening fades quickly. No dramatic solar flare. No headline-grabbing coronal mass ejection. Just a pulse, like the sun cleared its throat. Mainstream solar physics tells you that the sun runs on nuclear fusion in its core, converting hydrogen into helium and releasing immense energy in the process. Every second, about 600 million tons of hydrogen fuse together. That's not a typo. The sun loses around 4 million tons of mass per second, or converted directly into energy via Einstein's famous equation, E equals mc squared. And still, it has enough fuel to shine for about 5 billion more years. Talk about job security. So what's one tiny flicker in that vast furnace? Well, here's where things get interesting. The instruments detect a pattern embedded in the flicker, an oscillation that doesn't quite match typical solar flare signatures. Solar flares usually show a rapid spike and gradual decay in X-ray output. This one hums at a slightly different frequency, subtle, almost shy. Historians still argue whether ancient civilizations recorded unusual solar dimming events in myths of wounded suns or angry sky gods. Chinese astronomers meticulously documented sunspots as early as 28 BCE, noting dark marks visible to the naked eye during dusty sunsets. Yet those records now help modern scientists reconstruct long-term solar cycles. It turns out your ancestors were doing space weather reporting without even realizing it. And speaking of cycles, the sun operates on an approximately 11-year solar cycle, swinging from solar minimum, calm and relatively spot-free, to solar maximum, when sunspots and flares become more common. The current cycle has already surprised researchers by ramping up faster than predicted. That alone has scientists adjusting their models. But this flicker doesn't align neatly with the cycle's expectations. You picture the sun's surface not as a smooth ball of fire, but as a churning ocean of plasma. Magnetic field lines twist and tangle like spaghetti in zero gravity. When they snap and reconnect, they release enormous bursts of energy. It's magnetic reconnection, one of the most powerful processes in the solar system. Usually it's loud, dramatic, obvious. This wasn't. Instead, the data shows a contained release, energy vented without a full magnetic eruption, like a pressure valve that opened just enough to prevent a bigger blast. Convenient. Suspiciously convenient. Here's a quirky tidbit. In the 19th century, some scientists genuinely believed sunspots were holes in the sun's luminous shell, revealing a cooler, possibly even inhabited interior. Imagine pitching that research grant today. Yes, we believe there may be solar residents. They prefer warmer climates. You allow yourself a small, sleepy smile. Back in the observatory, the analysts run the numbers again. Instrument error, cosmic ray interference, a satellite hiccup. Space hardware is notoriously dramatic. One charged particle zips through a sensor and suddenly it's existential crisis time. But the signal appears across multiple instruments, different satellites, different angles. That's when the room gets quieter. Not alarmed, just attentive. Because the sun isn't supposed to surprise you in small ways. Big flares? Sure. Massive ejections? Absolutely. But subtle deviations in its internal rhythm, those are harder to categorize. Historians still argue whether our understanding of the sun is overly shaped by the relatively stable period of human civilization. After all, 10,000 years of calm is nothing compared to a 4.6 billion year lifespan. You're essentially judging an ocean by watching a single ripple. You lean back in your chair, at least in your imagination, and let the hum of equipment blend with the soft rush of solar wind streaming past Earth at about 400 kilometers per second. You don't feel it. Your atmosphere shields you. Your magnetic field deflects most of it. You're blissfully unaware of the constant stellar breath washing over your planet. And yet today, that breath hitched. Just slightly. The flicker fades from the live feed, archived into terabytes of solar history. Tomorrow's headlines will talk about politics, celebrities, maybe a new diet trend involving fermented algae. The sun's quiet anomaly won't trend on social media. It rarely does. But somewhere inside that roiling sphere of plasma, something shifted, released, adjusted. And whether it was a harmless magnetic hiccup or the first whisper of a deeper change, well, that's what you're here to find out. You keep watching the light, because the sun may look steady, but it just blinked. You don't look away from the light, you just change how you look at it. Instead of staring directly at that blazing disk, please don't, your retinas would file a formal complaint, you step sideways in time. You find yourself standing beside Galileo in 1610, squinting at a projected image of the sun trembling faintly on a sheet of paper. The room smells like ink and hot wax. Outside, Italy hums with Renaissance ambition. Inside, a man sketches dark specks crossing the sun's face. Those specks, sunspots, were controversial. The prevailing belief in Europe held that celestial bodies were perfect and unblemished. So, when Galileo and others reported imperfections, it wasn't just astronomy, it was philosophical rebellion. Mainstream historical fact. Galileo's sunspot observations helped undermine the idea of heavenly perfection and supported the concept of a dynamic, rotating sun. You can almost hear the collective gasp of 17th century scholars clutching their robes. Historians still argue whether Galileo was the very first European to observe sunspots through a telescope, or whether contemporaries like Christoph Scheiner beat him to publication by mere months. Academic rivalries, it turns out, are eternal solar flares of their own. You drift forward another century. Telescopes improve. Filters are invented so observers don't accidentally sacrifice their eyesight for science. A gentle reminder that curiosity is admirable, but blindness is inconvenient. By the 1800s, systematic sunspot records become more common. In 1843, amateur astronomer Heinrich Schwabe announces something remarkable. Sunspots rise and fall in a roughly 10-year cycle, later refined to about 11 years. That discovery lays the foundation for our understanding of the solar cycle. Imagine realizing that the sun has moods. Now you glide into the 20th century. The air smells faintly metallic and modern. Telescopes grow enormous. Mount Wilson Observatory peers at the sun with increasing precision. In 1908, George Ellery Hale discovers that sunspots are regions of intense magnetic activity. That's the moment magnetism enters the story like a plot twist. The sun isn't just hot gas. It's electrically alive, threaded with invisible magnetic lines that twist, tangle, and snap. Fast forward again, when suddenly you're weightless. You're orbiting Earth aboard a satellite because that's where serious solar watching happens now. The atmosphere, lovely as it is, blocks most ultraviolet and X-ray radiation, which is excellent for your skin, less excellent for solar physicists. So humanity launches observatories into space. In 1995, the SOHO spacecraft, Solar and Heliospheric Observatory, takes up position at a gravitational balance point between Earth and the Sun. It's been watching ever since, like the most dedicated security guard in the solar system. Fun fact, SOHO has discovered thousands of comets grazing the Sun, earning it an unexpected side hustle as a comet hunter. Not bad for a spacecraft that never comes home. You float past the Solar Dynamics Observatory, launched in 2010, capturing images in multiple wavelengths every few seconds. The sun appears in false colors, electric blues, molten golds, ghostly purples, each color representing different temperatures and energies. It looks less like a simple star and more like a living organism under a cosmic MRI scan. And this is how that flicker from Section 1 was caught. Not by one eye, but by a fleet of them. There's something soothing about the redundancy. Multiple satellites cross-checking each other. If one instrument glitches, another confirms or denies it. Space hardware can be temperamental. Cosmic rays zip through electronics and cause what engineers politely call single-event upsets, which is a charming way of saying, a particle from deep space just poked our computer in the brain. But this anomaly, it appeared across instruments. Actually, you settle into a control room again. Analysts scroll through data streams, magnetograms mapping magnetic fields, chronograph images blocking out the sun's bright disk to study the faint corona, spectrographs breaking light into precise wavelengths. The hum of servers feels almost meditative. Mainstream fact. The sun's corona is millions of degrees hotter than its surface, a puzzle known as the coronal heating problem. Scientists have debated for decades why this outer atmosphere is so blisteringly hot. Tiny magnetic reconnection events, nicknamed nanoflares, are one leading explanation. Historians still argue whether nanoflares alone can account for the corona's extreme temperature, or whether wave heating mechanisms play a larger role. It's one of those polite, ongoing scientific disagreements where no one flips tables. But everyone brings very persuasive graphs. Now here's a quirky tidbit for your sleepy brain. During the Cold War, the U.S. military monitored solar flares not out of pure curiosity, but because intense solar activity could interfere with radar systems. Solar physics and national security became unlikely companions. Somewhere a general once cared deeply about sunspots. You let that sink in. The anomaly you're tracing didn't look like a standard flare. It didn't erupt with dramatic plasma loops or blast a coronal mass ejection toward Earth. Instead, it resembled a localized brightening paired with a peculiar magnetic oscillation, like a plucked string vibrating slightly off-key. You zoom in on magnetogram data. The sun's surface resembles a shifting map of positive and negative magnetic regions. Normally, iso changes unfold gradually or explode spectacularly. This one did neither. It adjusted, and the adjustment was brief enough that, if you blinked, if a satellite had been in calibration mode, if a sensor had been temporarily offline, you might have missed it. That's the unsettling part. Humanity has only been observing the sun with advanced instruments for a few decades. A blink in cosmic time. You're building models based on a narrow slice of stellar behavior. It's like judging someone's personality after watching them for 5 minutes at a dinner party. Maybe they're calm. Maybe they're just tired. Historians still argue whether we're currently in an unusually stable solar period compared to ancient epochs. Ice core data and tree rings hint at past variations in solar output. Carbon-14 spikes in tree rings, for instance, have been linked to extreme solar particle events centuries ago. The famous Miyake event of 774 to 775 CE caused a dramatic increase in atmospheric carbon-14, likely from a massive solar storm. No tweets, no breaking news, just trees quietly recording the chaos. You imagine ancient forests absorbing sunlight while the sun briefly raged overhead. Silent witnesses. Back in orbit, modern instruments record something quieter, but still peculiar. The analysts overlay datasets, X-ray flux, ultraviolet intensity, magnetic field strength, particle counts. The lines don't diverge wildly, they nudge, just enough to raise eyebrows. And you can almost feel the collective scientific instinct. Don't overreact. Don't sensationalize, double check, triple check, because science isn't about drama, it's about patience. Still, patience doesn't eliminate curiosity. You lean closer to the scrolling data. The sun, that seemingly constant companion in your sky, is more dynamic than any bonfire or light bulb could ever be. It's a self-gravitating sphere of plasma, fusing atoms under crushing pressure, governed by equations that stretch across quantum mechanics and magnetohydrodynamics. And despite centuries of watching, from Galileo's ink-stained fingers to orbiting observatories humming in the vacuum, you're still catching it in moments of surprise. The flicker wasn't loud, it wasn't catastrophic, it was simply unanticipated. And sometimes in science, the smallest deviations are the ones that keep you awake at night. Or in your case, gently drifting towards sleep while the sun keeps humming, just slightly off key. You keep your eyes on the data stream, and now the sun decides to clear its throat a little louder. Not a roar, not the kind of solar tantrum that fries telegraph wires like it did during the Carrington event of 1859. That story is coming later. This is subtler, stranger, a flare that technically qualifies as a flare, but behaves like it didn't read the manual. Solar flares, in the mainstream textbook sense, are sudden releases of energy caused by magnetic reconnection in the sun's atmosphere. Twisted magnetic field lines snap and realign, releasing energy equivalent to millions of hydrogen bombs in minutes. They're classified by X-ray brightness, A, B, C, M, and X class, with X being the heavyweights. It's less of a grading system and more of a "how worried should we be" scale. This particular flare barely scraped into mid-level territory. On paper, unremarkable. When the kind of event space weather forecasters log with a calm sip of coffee. But when you replay the X-ray curve, something feels off. Normally, a flare's intensity spikes sharply, like a drum hit, and then decays gradually. Clean rise, slow fall. This one rises in two steps. A stutter, a hesitation in the energy release. Imagine clapping once and hearing a faint echo that shouldn't exist. You zoom in further. The first pulse is standard magnetic reconnection behavior. The second pulse arrives milliseconds later, slightly offset in frequency. Not random, structured. Historians still argue whether early flare classifications oversimplified the diversity of solar eruptions, grouping together events that may arise from subtly different magnetic configurations. In other words, maybe we've been calling very different solar tempers by the same name. You float above the sun's surface in your imagination. The photosphere below you churns like boiling oatmeal, except each bubble is the size of Texas. Convection cells rise and fall, carrying heat from the interior. Above that, magnetic loops arc high into the corona, glowing in ultraviolet light. In 1859, British astronomer Richard Carrington observed a sudden bright flash on the sun through his telescope, one of the first recorded solar flares. Hours later, Earth's magnetic field convulsed. Telegraph systems sparked. Auroras lit up skies as far south as the Caribbean. Mainstream fact: the Carrington event remains the most powerful geomagnetic storm on record. If a similar event hit today, it could cause widespread power outages and satellite damage. Now, your current flare isn't anywhere near that scale. It's more like the sun tapping a microphone and saying, "Testing, testing." but it's the waveform that keeps you leaning forward. Analysts compare it to known flare templates. They overlay historical data. Most flares fit predictable patterns shaped by magnetic reconnection models. This one shows an additional oscillatory component, a brief quasi-periodic pulsation embedded in the burst. Quasi-periodic pulsations, or QPPs, are actually known phenomena. They've been observed before. But here's the twist. The frequency of this one doesn't align neatly with standard magnetohydrodynamic wave predictions. It's slightly outside expected parameters. Not wildly, just enough to nudge scientists into that thoughtful silence again. Historians still argue whether QPPs are caused primarily by magnetohydrodynamic oscillations in coronal loops or by repetitive magnetic reconnection events in rapidly restructuring fields. Two mechanisms, both plausible, neither fully satisfying. You picture magnetic loops like taut rubber bands stretching thousands of kilometers above the sun. When they snap and reconnect, plasma surges along them at incredible speeds. Now imagine one loop interacting with another at just the wrong angle, like two guitar strings brushing. Could that create the secondary pulse? That's one mainstream hypothesis, but there's also a quieter murmur in the research community. Some solar physicists have proposed that certain flare anomalies might be influenced by deeper magnetic structures rooted far below the photosphere, structures we can't directly see. The sun's dynamo, the mechanism generating its magnetic field, operates deep within the convection zone. Turbulent plasma flows twist magnetic lines into massive toroidal bands. If something shifts down there, the surface might only show a subtle symptom. Here's a quirky historical tidbit. In the early 20th century, some researchers speculated that planetary alignments could trigger solar flares. The gravitational influence of Jupiter, they suggested, might tug on the sun's plasma. Modern calculations show planetary tidal forces on the sun are minuscule compared to internal forces. So no, Mercury is not secretly poking the sun with a cosmic stick. Still, the idea pops up every so often, because humans love patterns, especially dramatic ones. Back in the present, the flare's particle emissions are analyzed. Energetic protons and electrons stream outward, but in lower quantities than expected for even a mid-level flare. It's as if the energy release was partially contained. Contained flares aren't unheard of. Some eruptions fail to produce coronal mass ejections because overlying magnetic fields act like a lid, trapping plasma. But this one seems almost deliberately restrained, a flare that flexed, then stopped itself. You imagine the sun practicing self-control, which is adorable and scientifically inaccurate, but comforting. The magnetograms reveal a region of complex polarity, positive and negative fields pressed tightly together. Beta-gamma-delta classification. In solar jargon, that's a messy magnetic neighborhood. These regions are known for flare production. But even messy neighborhoods follow certain rules. This flare bends them slightly. Historians still argue whether our flare models, built heavily on statistical averages, miss rare subtypes that could reveal new physics. After all, outliers are where discoveries hide. Pulsars were once scruff in radio data. Fast radio bursts were mysterious blips before they became a research goldmine. You lean back and let that idea settle. Maybe this flare is nothing more than a rare configuration of known processes. A magnetic hiccup, a statistical oddball. Science thrives on those. Or maybe it's a small window into something deeper, an adjustment in the sun's internal magnetic rhythm that only occasionally surfaces as a strange double pulse. Outside, Earth continues spinning peacefully. Birds migrate, coffee cools, traffic lights change on schedule. The sun shines, apparently indifferent. But in orbital silence, instruments hum. Data accumulates, analysts annotate, and you, drifting in this observatory of the mind, feel the gentle thrill of uncertainty, not fear, just curiosity wrapped in warm starlight. Because the flare didn't explode, it hesitated. And sometimes hesitation tells you more than chaos ever could. The sun has cleared its throat, softly, twice. You let the flare's echo fade into the background, and your attention shifts slightly left, toward the dark freckles scattered across the sun's face. Sunspots. They look harmless enough in photographs. Little smudges, ink drops on a golden canvas. But each one is a region of intense magnetic activity, cooler than the surrounding surface by about 1,500 degrees Celsius. Cooler is relative, of course, and they're still hot enough to vaporize absolutely everything you've ever owned, including that drawer of mysterious cables you refuse to throw away. Mainstream fact, sunspots follow an approximately 11-year solar cycle, rising from solar minimum, when the sun is relatively smooth, to solar maximum, when sunspots can number in the hundreds. This cycle was first identified in the 19th century by Heinrich Schwabe and later linked to magnetic polarity reversals by George Ellery Hale. Every 11 years, activity peaks. Every 22 years, the sun's magnetic poles fully flip and return to their original orientation. Yes, the sun has a magnetic identity crisis every couple of decades. You hover over the latest solar imagery. The current cycle has been ramping up faster than predicted. Forecast models expected a modest maximum. Instead, sunspot counts are climbing ahead of schedule, not alarmingly, but confidently, like the sun showed up early to its own party. And within this rising tide of spots, one cluster stands out. It's large, complex, a tangled knot of magnetic polarity. Beta gamma delta classification again, the kind of region known to produce flares. That strange double-pulsed flare from earlier? It came from here. You zoom closer. Sunspots aren't flat stains. They're depressions in the photosphere caused by magnetic fields suppressing convection. Plasma can't rise as easily, so the region cools slightly and darkens. Around each dark core, the umbra, there's a lighter penumbra with filament-like structures radiating outward. They're beautiful in a dangerous sort of way, like cosmic whirlpools. Historians still argue whether early telescopic drawings underestimated the complexity of sunspot structure due to optical limitations. When you compare Galileo's simple circles to modern high-resolution imagery, it's like comparing a stick figure to a Renaissance painting. Now here's a quirky tidbit. In ancient China, large sunspots were occasionally visible to the naked eye during heavy dust storms or at sunrise and sunset. Court astronomers recorded these black spots as omens. Some interpretations link them to political upheaval. Imagine blaming a patch of magnetized plasma 150 million kilometers away for your tax policy problems. Honestly, it's almost comforting. Back in the present, scientists aren't looking for omens. They're looking for patterns. The odd thing about this sunspot cluster isn't just its size, it's its orientation. Normally, sunspots follow something called Hale's law. During a given solar cycle, leading sunspots in one hemisphere share the same magnetic polarity, and the opposite hemisphere mirrors that pattern. It's part of the sun's grand magnetic choreography, but this cluster shows slight deviations in tilt, subtle angular differences from Joy's law, which predicts how sunspot groups tilt relative to the solar equator. The tilt isn't wildly wrong, it's just off. Historians still argue whether deviations from Joy's law are random fluctuations in turbulent plasma or signs of deeper dynamo irregularities within the convection zone. In other words, is this statistical noise, or is the engine itself misfiring slightly? You imagine the sun's interior like a vast ocean of electrically conducting fluid, where plasma flows in enormous circulating currents. The differential rotation, where the equator rotates faster than the poles, stretches magnetic field lines over time, winding them tighter and tighter. Eventually, they buoyantly rise to the surface as sunspots. If the flow patterns deep below shift even a little, the geometry of emerging spots could change. And that's what you're seeing. Geometry with a personality quirk. The cluster rotates into full view as the sun turns on its axis. About once every 27 days as seen from Earth. That rotation itself was confirmed centuries ago through sunspot tracking. You're watching the same method, just with better cameras and fewer powdered wigs. The magnetic map shows shear along the boundary between opposite polarities. Shear is tension. Tension stores energy. Energy looks for a way out. When that's textbook flare territory, yet the flare you observed earlier didn't fully release that tension. It was as if the region exhaled instead of shouting. You scroll through historical sunspot records. During particularly active cycles, like solar cycle 19 in the late 1950s, sunspot numbers soared to some of the highest levels ever recorded. That cycle produced powerful geomagnetic storms and dazzling auroras. The current cycle isn't breaking records yet, but it's exceeding expectations. Historians still argue whether predictive models for solar cycles are fundamentally limited because the solar dynamo is a chaotic system. Small changes in plasma flow can cascade unpredictably. It's weather forecasting, but inside a star. You let that sink in, forecasting a star. No wonder surprises slip through. Now, onto another curious detail. This sunspot cluster appears to have emerged unusually quickly. The growth rate, measured in millionths of the solar hemisphere, is steeper than average. Rapid emergence suggests strong magnetic flux tubes rising from deep within the convection zone. Strong tubes mean strong fields. Strong fields mean potential for powerful events. And yet, instead of a dramatic eruption, you got a hesitant flare and a contained release. It's like loading a spring, watching it compress, and then seeing it release just a fraction of its stored energy. You tilt your head, figuratively, because you're floating in space again. The sun glows steady and indifferent. The cluster continues its slow march across the disk. There's something almost theatrical about it. A build-up without climax, suspense without explosion. And that's what makes scientists uneasy. Not because it's dangerous right now, but because it challenges the rhythm they're used to. Patterns are comforting. Even chaotic systems have statistical personalities. But when a familiar pattern bends, just slightly, it forces you to ask whether the rules are shifting or whether you're only now noticing complexities that were always there. The sun doesn't announce its secrets with fireworks every time. Sometimes it rearranges its freckles and waits to see if you're paying attention. You drift outward now, beyond the dark freckles and hesitant flares, into the sun's outer atmosphere, the corona, where things stop pretending to be subtle. This is where coronal mass ejections are born. A coronal mass ejection, or CME, is not just a flare with better marketing. Why, it's a colossal expulsion of plasma and magnetic field from the sun's corona into space. Billions of tons of charged particles hurled outward at speeds that can exceed 2,000 kilometers per second. If solar flares are lightning, CMEs are hurricanes made of magnetized fire. Mainstream fact: CMS are the primary drivers of major geomagnetic storms on Earth. When a CME slams into Earth's magnetosphere, it can compress the magnetic field, induce electric currents in power lines, disrupt satellites, and produce spectacular auroras. You imagine one launching. A magnetic loop stretches higher and higher above the sun's surface, like taffy pulled too thin. Beneath it, magnetic reconnection rearranges field lines in a sudden explosive shift. The loop destabilizes. Plasma, superheated, electrically charged, erupts outward. Are carrying embedded magnetic fields with it. It's violent, it's luminous, it's usually unmistakable. But the event tied to your strange flare? It produced something smaller, a faint CME, a partial halo in coronagraph imagery. Not the kind that triggers emergency meetings at power grid control centers. More like a shrug than a punch. You float beside a space-based coronagraph, its disk blocking the sun's bright face so the faint corona becomes visible. Against the darkened backdrop, you see the ejection bloom outward, uneven, asymmetrical. It doesn't expand in a smooth circular wave. It warps slightly to one side, as though guided by invisible rails. Historians still argue whether asymmetries in CMEs are primarily caused by surrounding coronal magnetic structures or by instabilities within the erupting flux rope itself. Is the environment steering the blast, or is the blast inherently lopsided? You watch the plasma cloud stretch as it travels, the sun's rotation giving it a subtle spiral twist. This spiral shape, known as the Parker spiral, is a natural result of the sun rotating while emitting the solar wind. Discovered by physicist Eugene Parker in the 1950s, it's now a foundational concept in heliophysics. Picture a rotating lawn sprinkler flinging water outward. That's your star. Here's a quirky tidbit. When CMEs were first observed in the early 1970s by space-based coronagraphs, scientists weren't entirely sure what they were seeing. Some initially thought the bright arcs were instrumental artifacts. It took repeated observations to confirm they were genuine solar eruptions. Even in space science, the first reaction to something new is often, "Oh, is the camera broken?" Now you examine the magnetic orientation embedded in this particular CME. That's crucial. If the CME's magnetic field aligns southward relative to Earth's magnetic field, it can more easily connect and transfer energy, like two magnets snapping together. If it's northward, the interaction is weaker. This one? Mostly northward. Convenient, almost too convenient. The plasma density is moderate. The speed is respectable but not record-breaking. Space weather models predict only minor geomagnetic disturbances as it passes Earth. And indeed, when it arrives days later, Earth's magnetosphere flexes gently. A mild aurora blooms near polar regions. Satellites register minor fluctuations. Nothing dramatic. But you're not focused on the impact. You're focused on the origin. The flare was odd. The sunspot cluster was slightly misaligned. And now the CME is restrained. Energetic enough to qualify, but not proportional to the magnetic tension observed in that active region. It's like watching someone wind up for a fastball and then toss a paper airplane. Historians still argue whether our current CME initiation models fully account for the complexity of three-dimensional magnetic topology in active regions. Most models rely on simplified geometries. Reality, as always, is messier. You descend closer to the corona in your imagination. The temperature here soars to millions of degrees. The plasma is so tenuous it would count as a better vacuum than most laboratory chambers on Earth. And yet it glows, structured by magnetic fields you can't see but can infer from motion. In the CME's flux rope, the twisted magnetic core of the ejection appears slightly kinked, not dramatically unstable but bent. Kink instability is a known phenomenon in plasma physics, where twisted magnetic structures can become unstable if the twist exceeds a critical threshold. Did this flux rope approach that threshold and then stop short? You replay the data again. The flare's double pulse, the contained energy release, the asymmetrical CME, the mostly northward magnetic orientation. Each detail alone is ordinary. Together, they feel curated. Now you resist the temptation to assign intention. The sun is not plotting. It's not hiding secrets behind a fiery curtain. It obeys physics, complex, nonlinear, chaotic physics, but physics nonetheless. And yet, historians still argue whether rare stealth CMEs, ejections with minimal low coronal signatures, are undercounted because they're harder to detect. Some CMS leave almost no obvious flare behind. In this case, you have the opposite. A noticeable flare with a surprisingly modest ejection, a reversal of expectations. You let your mind wander briefly to 1989, when a powerful geomagnetic storm caused a blackout in Quebec, leaving millions without power for hours. That storm was triggered by a CME interacting strongly with Earth's magnetic field. It was a reminder that even our modern infrastructure bows to solar tempers. This time, infrastructure barely noticed, which is good, comforting, and still faintly puzzling. The CME continues outward, expanding, thinning, merging with the ambient solar wind. By the time it reaches the orbit of Mars, it's a stretched ghost of its former self. Behind it, the sun resumes its steady glow. The active region persists, rotating slowly across the disk. Magnetic fields continue to writhe, and you're left with a pattern. Energy stored, partially released, partially withheld. Not an explosion, a controlled exhale. The sun didn't lash out, it vented. And somewhere in that restraint, in that measured release, lies the question you can't quite shake. Was this just an ordinary imbalance resolving itself? Or did the sun deliberately avoid something bigger? Not intentionally, of course, but physically, as though a deeper instability flickered, and then settled back into the fire. You move deeper now, not into the bright violence of flares or the sweeping drama of coronal mass ejections, but into something quieter and far more powerful, the sun's magnetic field. If the sun were just a ball of hot gas, it would be complicated enough. But it isn't. It's plasma, electrically charged fluid, and constantly in motion. And wherever charged particles flow, magnetic fields bloom. Mainstream fact: the sun's magnetic field is generated by a dynamo process inside its convection zone, where hot plasma rises, cools, sinks, and rotates at different speeds depending on latitude. This differential rotation, faster at the equator, slower at the poles, twists magnetic field lines over time, amplifying and restructuring them. Picture taffy being pulled unevenly on a spinning plate. Now picture that taffy made of electricity. You descend in your imagination beneath the photosphere, below the visible surface. It's into the convection zone, a region extending roughly 200,000 kilometers downward. Plasma churns here in colossal circulating currents. These flows stretch and wrap magnetic field lines into toroidal bands that encircle the sun like invisible belts. Every 11 years or so, those belts become unstable, buoyantly rising through the surface as sunspots. Every 22 years, the global magnetic polarity flips entirely. North becomes south. South becomes north. No drama, just a planetary-scale magnetic reset. If Earth did that every couple of decades, compasses would need therapy. Now the anomaly you've been tracing, the odd flare, the restrained CME, the misaligned sunspot cluster, leads you to examine the magnetic topology more closely. Magnetic topology is just a fancy way of saying, how are the field lines arranged in three-dimensional space? Why don't you float above a magnetogram, an image mapping magnetic polarity across the sun's surface? Red for positive, blue for negative. The active region looks like spilled paint, colors pressed tightly together. But there's something else, a subtle kink in the overlying magnetic arcade, the large-scale loops arching above the active region. These loops usually form smooth, elegant curves. Here one appears slightly twisted, almost braided. Historians still argue whether large-scale coronal magnetic fields can store significantly more energy than surface measurements alone suggest. Surface magnetograms give you a two-dimensional slice, but the true structure is three-dimensional and notoriously difficult to reconstruct. You imagine invisible ropes suspended above the sun, woven and layered. Some loops anchor deep into the convection zone. Others connect distant regions across thousands of kilometers. And here's where it gets interesting. Recent modeling suggests that small perturbations deep in the dynamo layer, subtle shifts in plasma flow speed or direction, can ripple upward and alter magnetic emergence patterns months later. It's like nudging the base of a lava lamp and waiting for the blobs to reorganize. The kink you're observing might be the surface echo of something deeper. Now, a quirky tidbit. In the 1970s, some physicists briefly explored whether exotic particles, like hypothetical magnetic monopoles, could influence stellar magnetic behavior. Magnetic monopoles, particles with only one magnetic pole, have never been confirmed experimentally. But the idea lingered long enough to inspire some delightfully speculative papers. No. And the sun is not secretly hoarding monopoles? Probably. Still, it's charming how even stars invite creative thinking. You examine the timing of the magnetic tension buildup. The active region developed rapidly. The flare released some energy. The CME vented a portion. But post-event magnetic field measurements show that not all the stored energy dissipated. That's the key detail. After major flares, magnetic fields typically relax into simpler configurations. The tension decreases noticeably. In this case, the reduction is partial. The system remains complex. Historians still argue whether partial energy releases indicate failed eruptions, situations where magnetic flux ropes attempt to destabilize but are confined by stronger overlying fields. In such scenarios, the sun almost erupts, and then doesn't. Almost. Watch you replay the magnetic evolution frame by frame. The kink in the coronal loop intensifies slightly before the flare. Afterward, it smooths, but not completely. It's like a twisted rubber band that was stretched, released a little tension, and then stayed coiled. Now you consider magnetic helicity, a measure of how twisted and intertwined magnetic field lines are. Helicity is conserved in many plasma systems. It doesn't just vanish, it redistributes. If the flare in CME didn't remove enough helicity, where did the excess go? Perhaps it shifted into adjacent loops. Perhaps it sank deeper into the solar interior. Perhaps it's waiting. The sun's magnetic field isn't static. It's a living architecture, constantly rebuilt by plasma flows you can't directly observe. You infer its structure from light and motion, and not from spectroscopy and polarization measurements. And sometimes those inferences don't align perfectly. Historians still argue whether current dynamo models fully capture the role of meridional circulation, the slow flow of plasma from equator to poles and back again at depth. Variations in this flow could alter the timing and intensity of solar cycles. Small changes, big consequences. You let the scale of it settle around you. Beneath that bright, familiar disk is a self-organizing electromagnetic engine, operating on scales that dwarf comprehension. Magnetic loops larger than planets, currents flowing for years, instabilities forming, resolving, reforming. And somewhere in that grand choreography, a kink formed. It tightened, it partially released, and it remains, slightly misaligned with expectations. The sun didn't explode, it adjusted. Like a dancer correcting balance mid-performance. The question isn't whether magnetic fields twist. They always do. The question is whether this particular twist is routine chaos in a turbulent star, or a sign that the deeper dynamo rhythm has shifted, even slightly. You hover there in the glow of invisible lines, feeling the quiet tension humming beneath the surface. Because sometimes the loudest secrets aren't in the explosions, they're in the knots that don't quite untangle. You don't chase explosions now. You sit with the numbers. Because sometimes the sun doesn't shout, it whispers in data. Inside a quiet operations room, far from the blaze of the corona, analysts scroll through waveforms that look, at first glance, like ordinary noise. Jagged lines, minor fluctuations. And the kind of thing you'd ignore if you didn't know that buried inside those lines is the behavior of a star 150 million kilometers away. Mainstream fact: solar monitoring relies on continuous streams of data across multiple wavelengths, radio, visible light, ultraviolet, X-ray, as well as in situ particle detectors measuring the solar wind. These datasets are immense, often terabytes per day, and much of the anomaly detection is automated through algorithms trained to flag unusual deviations, which means, ironically, that a machine noticed the whisper before a human did. You imagine the algorithm pausing, metaphorically, on a small irregular oscillation in radio flux, a spike too structured to be random, too brief to be dramatic. It flags the segment for review. A human leans closer. The waveform isn't large, it's patterned. And solar radio emissions often accompany flares in CMEs. They're categorized into types. Type 2 bursts associated with shock waves, Type 3 bursts linked to energetic electron beams traveling along magnetic field lines. These bursts have characteristic frequency drifts as particles move through plasma of varying density. But this signal doesn't fit neatly into those categories. It's narrowband, short-lived, and rhythmically modulated. Historians still argue whether certain rare radio bursts, sometimes called decimetric spikes, are generated by plasma instabilities in small-scale magnetic reconnection sites or by wave-particle interactions in turbulent regions of the corona. Both mechanisms can produce rapid oscillations. Neither fully explains every observation. You replay the data. There it is again. A faint oscillation at a frequency slightly offset from expected plasma emission lines. Not wildly wrong, just displaced. Now here's a quirky tidbit. In 1967, when Jocelyn Bell Burnell first detected a regular pulsing radio signal from space, it was so precise that researchers briefly labeled it LGM1 for Little Green Men. It turned out to be the first discovered pulsar, a rapidly rotating neutron star. The lesson? Sometimes strange signals aren't aliens. They're new physics. Relax. The sun has not begun broadcasting coded messages, but the memory lingers in every scientist who sees something unfamiliar. Check everything before you panic. You examine the plasma density models for the active region. Radio emission frequencies depend on electron density in the corona. If density estimates are slightly off, predicted frequencies shift. Could that explain the offset? Maybe. Except the density measurements from extreme ultraviolet imaging suggest normal values for a region of that temperature. So you widen the search. You overlay magnetic field extrapolations, models that estimate three-dimensional coronal fields from surface magnetograms. The unusual oscillation coincides spatially with the kinked magnetic arcade you noticed earlier. Coincidence is common in chaotic systems, but patterns cluster. Historians still argue whether our coronal magnetic field extrapolation techniques, like nonlinear force-free field models, accurately capture small-scale current sheets where reconnection occurs. These models rely on assumptions that may oversimplify real plasma behavior. In other words, your map of invisible magnetic space might be slightly blurry. The oscillation persists for only seconds. Then it vanishes into background noise. If you weren't looking for it, if you weren't already primed by the double pulse flare and restrained CME, you might dismiss it as instrumentation artifact. So you check the instruments. Multiple radio observatories detect the same feature. Ground-based arrays, space-based receivers, independent systems, different calibration pipelines. The signal is real. You feel that quiet tightening again. Not fear, just attention sharpening. The sun emits constant radio noise from thermal plasma. It crackles like a cosmic fireplace. But this was tonal, almost musical in structure. A faint tremor in the symphony. There's another detail. The oscillation frequency drifts slightly upward over its short lifespan. And that suggests the source region is moving into lower density plasma, possibly upward through the corona. So something rose. Not explosively, not like a full CME shock front. Something smaller. You picture a localized magnetic island, what plasma physicists call a plasmoid, forming in a current sheet during reconnection. Plasmoids can detach and move outward, producing short radio signatures. Mainstream models predict them in high-resolution simulations. Observational confirmation has been growing in recent years. Could this be one? Possibly. But the periodic modulation layered on top of the signal complicates things. It suggests oscillatory reconnection, bursts of reconnection happening in rapid succession rather than one smooth event. Historians still argue whether oscillatory reconnection is a common but under-resolved feature of solar flares. Hidden by instrument cadence limits, faster detectors have revealed more fine structure in recent years. Meaning, maybe the sun has always done this. You just couldn't see it before. There's something humbling about that thought. For centuries, you saw sunspots and thought they were holes, then magnetic storms, then plasma dynamics. Each technological leap revealed finer texture. Now high-cadence radio arrays and machine learning filters peel back another layer. The anomaly might not be new behavior. It might be newly visible behavior. Still, the timing aligns too neatly with everything else. The kinked magnetic field, the partial flare, the restrained CME, individually explainable, collectively intriguing. The oscillation fades. Data scrolls on. Solar wind streams past at its steady pace. The sun radiates its familiar warmth toward Earth, utterly indifferent to your curiosity. But you remain in that quiet room, bathed in monitor glow, listening to the after echo of a star's whisper. Because sometimes the most important signals aren't the loudest. They're the ones almost lost in noise. Until you decide to listen more carefully, you let the modern monitors dim in your mind, and instead you light a lantern. Not metaphorically, well, yes, metaphorically, but also historically. You step back into a world without satellites, without radio arrays, without algorithms scanning terabytes of solar data. Just ink, paper, and sky. Because if you want to understand whether this subtle solar event matters, you have to ask a simple question. Has the sun done stranger things before? Mainstream historical fact. On September 1, 1859, British astronomer Richard Carrington observed a sudden bright flash of white light on the sun. Within 18 hours, Earth's magnetic field convulsed. Telegraph systems sparked, operators received electric shocks, and auroras were seen as far south as Cuba and Hawaii. The Carrington event remains the strongest geomagnetic storm ever recorded. You imagine yourself standing under that sky. Curtains of red and green light ripple overhead, so bright you could read a newspaper at midnight. In some places, gold miners reportedly woke up thinking dawn had arrived. And here's the eerie part. The flare Carrington saw was visually dramatic, a blinding white patch in the sun's atmosphere. There was no subtlety about it, and no whisper. It shouted across space. Your current anomaly is nothing like that, but history doesn't only record the loudest screams. In 774 to 775 CE, something strange happened to Earth's atmosphere. Modern scientists discovered a sudden spike in carbon-14 levels preserved in tree rings worldwide. Carbon-14 increases when high-energy particles strike the atmosphere. The most widely accepted explanation? An extreme solar particle event, possibly even stronger than the Carrington event. Historians still argue whether the 774 event was caused by an unusually powerful solar flare, a sequence of solar storms, or a rare cosmic ray burst from a distant astrophysical source. The debate continues because written records from the time are sparse and ambiguous. You picture ancient scribes noting unusual auroras or red crosses in the sky, none unaware they were witnessing evidence of a stellar outburst powerful enough to leave fingerprints in trees for over a millennium. The sun has moods you only partially remember. There's also the so-called Miyake events, named after the researcher who identified those carbon-14 spikes. Another spike occurred around 993 CE. Again, likely solar in origin. Again, dramatic and atmospheric impact. And yet your current solar flicker produced no global isotope surge, no dazzling equatorial auroras, no telegraph wires bursting into flame, mostly because we replaced telegraph wires with fiber optics and satellites, which are far less romantic but much faster. Still, you ask yourself, is subtlety a sign of calm or of something building? Here's a quirky tidbit. In 1582, observers in Europe reported strange sky glows and halos around the sun. Some were likely atmospheric phenomena, ice crystals refracting light, but others may have coincided with solar activity. Before modern instrumentation, it was notoriously difficult to separate solar-driven auroras from optical illusions or even enthusiastic imagination. Humans are very good at seeing drama in the sky. Historians still argue whether certain medieval reports of blood-red heavens correspond to intense geomagnetic storms or were colored, quite literally, by symbolic language common in chronicles of the time. You step forward again into the early 20th century. The 1921 geomagnetic storm, sometimes called the New York Railroad Storm, disrupted telegraph and railway signaling systems. Fires broke out in switching stations. It wasn't quite Carrington level, but it was powerful. Then 1989. Quebec's power grid collapses for 9 hours after a CME-induced geomagnetic storm. 6 million people lose electricity. Transformers hum unhappily. Engineers scramble. Compared to those events, your present anomaly is gentle. A restrained flare, a modest CME, a whispering radio oscillation. But history teaches you something important. The sun does not always escalate gradually. Solar activity doesn't necessarily climb a neat staircase from small to large events. Sometimes quiet periods precede powerful outbursts. Sometimes active periods contain surprisingly tame releases. Historians still argue whether extreme solar storms cluster in particular phases of the solar cycle or occur more randomly than predictive models suggest. Statistical analyses offer probabilities, but not guarantees. What you imagine ancient farmers watching auroras ripple at latitudes where they rarely appear, unsure whether to pray, celebrate, or blame the neighbor. You imagine telegraph operators in 1859 unplugging equipment as sparks danced along copper wires. You imagine modern satellite controllers adjusting spacecraft orientation to minimize charged particle exposure. Each era meets the sun with the tools it has. Now it's your era's turn. The anomaly you're tracking hasn't harmed anything. It hasn't dazzled the skies at unusual latitudes. It hasn't left radioactive fingerprints in tree rings, at least none detected. But it carries echoes. The double pulse flare echoes the complexity of past extreme events, just scaled down. The kinked magnetic field echoes the tension that once unleashed massive storms. The radio whisper echoes the kind of particle acceleration that, in larger doses, can flood Earth's atmosphere. It's as if the sun rehearsed something, softly. You stand at the edge of history, comparing ink sketches to digital magnetograms. You feel the continuity, centuries of humans staring at the same star, trying to understand its rhythms. And one thing becomes clear. The sun has always surprised you, sometimes loudly, sometimes quietly. The difference now is that you have instruments sensitive enough to catch even the smallest deviations. You don't have to wait for telegraph systems to ignite or auroras to paint the tropics. You can see the tremor before the quake. Or at least you hope you can. The lantern dims. The monitors glow again. Past storms settle into archived data in tree rings and yellow journals. And you're left with a gentle but persistent thought. History shows the sun is capable of extremes. So when it behaves just slightly outside expectations, even in small ways, you pay attention. You return from lantern light and tree rings to something far more fragile, your Wi-Fi signal. Because while ancient auroras were beautiful inconveniences, modern civilization is electrically dramatic. You live inside a web of satellites, power grids, GPS timing signals, aviation routes, undersea cables, and orbiting metal boxes that absolutely do not enjoy being peppered with high-energy particles. Mainstream fact: a strong geomagnetic storm can induce currents in long conductors on Earth's surface, like power lines and pipelines, through a process called geomagnetically induced currents, GICs. These currents can overload transformers, yes, leading to blackouts. That's precisely what happened in Quebec in 1989. Now imagine explaining to someone in 1750 that a star 150 million kilometers away could knock out your refrigerator. You float upward into orbit again, where satellites glide in precise paths around Earth. GPS satellites carry atomic clocks so accurate they lose only about 1 second in millions of years. Your phone depends on them to tell you where you are, even when you insist you know a shortcut. Solar storms can disrupt that timing. When high-energy particles and X-rays from a flare hit Earth's upper atmosphere, they ionize it, charging it up, thickening certain layers of the ionosphere. Radio waves passing through can refract unpredictably. GPS accuracy can degrade. High-frequency radio used by aviation and maritime operators can fade or drop out entirely. And then there are satellites themselves. Energetic particles can penetrate spacecraft shielding, causing single-event upsets, tiny electronic hiccups when a charged particle flips a bit in memory. Usually harmless, occasionally inconvenient, rarely catastrophic. Historians still argue whether modern satellite constellations are more vulnerable to moderate but frequent solar storms than previously assumed, especially with the rise of large low Earth orbit fleets. More satellites mean more exposure, statistically speaking. You think back to the restrained CME from earlier. It arrived with mostly northward magnetic orientation, producing only mild geomagnetic effects. Earth's magnetosphere flexed, absorbed, and carried on. But here's what caught the analysts' attention. Even though the CME was modest, certain satellites reported slightly elevated particle flux in regions not typically associated with strong storms. Not alarming levels, just displaced zones of enhancement. Imagine rain falling lightly, but some puddles forming in odd places. The Van Allen radiation belts, two donut-shaped regions of trapped charged particles surrounding Earth, respond dynamically to solar input. During geomagnetic storms, these belts can swell, intensify, or shift. In this case, a minor rearrangement occurred, small, temporary, but slightly misaligned with predictive models. Historians still argue whether current radiation belt models adequately capture ultra-low frequency wave-particle interactions that can redistribute energetic electrons during even mild geomagnetic disturbances. Translation: Earth's magnetic shield is more complex than your textbooks promised. You hover at the boundary of Earth's magnetosphere, the magnetopause, where solar wind pressure meets planetary defense. Normally, during a modest CME impact, the magnetopause compresses slightly and then relaxes. This time, compression occurred in a somewhat asymmetric pattern. Not dangerous, just skewed. It's like watching someone gently press on a balloon and seeing it indent in an unexpected direction. Now here's a quirky tidbit. During strong solar storms, airlines sometimes reroute polar flights because communication blackouts can occur at high latitudes. Passengers might never know that a stellar outburst nudged their flight path a few hundred miles south. Somewhere, a pilot casually says, "Kiro, we're taking a slightly different route today," while the sun smolders quietly overhead. In your present case, no flights were rerouted. No grid operators sounded alarms. But space weather centers did log the event, because subtle anomalies matter when your civilization runs on electricity. You imagine a control room at a power grid operator's headquarters. Engineers monitor transformer loads, voltage stability, harmonic distortions. During major solar storms, they can reduce load, adjust configurations, even temporarily disconnect vulnerable components. This time, nothing required intervention. Still, the data from magnetometers scattered across Earth show faint, synchronized fluctuations. Geomagnetic pulsations slightly outside expected amplitude ranges for a storm of this classification. Historians still argue whether classification scales, like the NOAAG scale for geomagnetic storms, oversimplify complex, multi-parameter space weather effects. A storm labeled minor might still produce localized surprises. And that word again, surprises. You step back and look at the pattern forming. The sun's flare was slightly unusual. The CME was asymmetrical and restrained. The magnetic fields remained partially tense. A radio oscillation whispered unexpectedly. And Earth's magnetosphere responded, not dramatically, but with minor irregularities. Individually, each element fits within known physics. Collectively, they hum slightly off-key. You don't feel panic, you feel awareness. Modern society has built a delicate technological exoskeleton around itself. Satellites for communication, GPS for timing, financial transactions, and power grids optimized for efficiency rather than resilience against once-in-a-century solar tantrums. The sun doesn't need to unleash a Carrington-level event to test that system. Even moderate storms reveal stress points. But here's the comforting part. Earth's magnetic field is strong. Your atmosphere is thick. You are not about to be vaporized by a solar sneeze. Despite dramatic headlines you might see elsewhere, ordinary solar activity is a routine part of planetary life. You're still here, warm, breathing under a sky that filters out most of the sun's harshest radiation. And yet, as satellites hum overhead and magnetometers tick quietly in research stations near the poles, you realize something subtle. The sun nudged Earth, gently, and Earth answered, not with catastrophe, but with a response just slightly more complex than expected. The systems held, the grids stayed lit, the GPS kept guiding drivers who still ignored directions. But the data remains. And in the world of space weather, data is memory. You lean back and watch the sun continue shining with deceptive calm. Because the question isn't whether civilization survived this event. It did. The question is whether the sun is adjusting its rhythm in ways your models are only beginning to notice. And whether your delicate technological web is ready for the next variation in the song. You've watched the surface. You've traced the magnetic loops. You've followed plasma as it spilled into space and brushed Earth's magnetic shield. Now you do something far more ambitious. You go inside the sun. Not physically, of course. If you attempted that, you would be converted into enthusiastic plasma in less than a second, and which is not ideal for long-term planning. Instead, you descend through mathematics and particles, through something that passes through the sun as if it barely exists at all. Neutrinos. Mainstream fact. The sun produces an enormous number of neutrinos every second as a byproduct of nuclear fusion in its core. These nearly massless particles interact so weakly with matter that trillions pass through your body each second without you noticing. They are born in the core and escape almost instantly, reaching Earth in about 8 minutes, far faster than photons, which can take thousands to hundreds of thousands of years to random walk their way out from the core to the surface. Neutrinos are the sun's direct confession. Photons you see today began their journey long ago, bouncing around inside the radiative zone in a chaotic zigzag. But neutrinos, they come straight from the fusion furnace, which makes them incredibly valuable. In the late 1960s, scientists detected fewer solar neutrinos than predicted, a mystery known as the solar neutrino problem. For decades, physicists puzzled over the discrepancy. Historians still argue whether early skepticism leaned too heavily towards solar model errors before neutrino oscillations, where neutrinos change flavor en route to Earth, were fully confirmed. Eventually, experiments proved neutrinos oscillate between types, resolving the deficit and earning a Nobel Prize. The lesson: sometimes the sun isn't wrong. Your understanding is. Now you turn to modern neutrino observatories, vast underground detectors like Super Kamiokande in Japan or the Sudbury Neutrino Observatory in Canada. On huge tanks of ultra-pure water buried deep to shield them from cosmic noise. When a neutrino interacts, it produces a faint flash of light, Cherenkov radiation, a tiny blue whisper in the dark. You imagine sitting in that cavernous stillness, blue flickers in black water, the sun speaking through ghost particles. Here's where things get delicate. Following the strange flare and magnetic irregularities, a few researchers quietly check neutrino flux data. Not because they expect fireworks, solar fusion rates are extraordinarily stable, but because anomalies sometimes hide in cross-disciplinary corners. The sun's energy output is remarkably steady. Over decades, total solar irradiance varies by only about 0.1% across the solar cycle. Fusion in the core doesn't fluctuate dramatically on short timescales. It's governed by gravitational equilibrium, inward pressure balanced by outward radiation. But neutrino measurements are sensitive to subtle shifts in fusion processes. And there, barely above statistical noise, is a minute variation in detected neutrino counts. Not dramatic, not headline-worthy, just slightly above rolling average expectations for that month. Historians still argue whether short-term fluctuations in neutrino detection rates reflect true solar variability or statistical and instrumental uncertainties. Even massive detectors have error bars. Tiny differences can vanish with further calibration. You check calibration logs, no obvious issues. The variation is small, fractions of a percent, within theoretical bounds but nudging the upper edge. Now, to be clear, this does not mean the sun's core suddenly hiccuped. When nuclear fusion in the sun operates on timescales and pressures that resist rapid swings, any meaningful change in core fusion rate would take thousands of years to affect surface luminosity. But neutrinos are immediate. If something altered reaction chains slightly, even temporarily, you might see it in neutrino flux before anywhere else. You recall the primary fusion pathway in the sun, the proton-proton chain. Hydrogen nuclei fuse into helium through a series of steps, releasing positrons, neutrinos, and energy. There's also a minor contribution from the CNO cycle, carbon-nitrogen-oxygen catalyzed fusion, which becomes more dominant in heavier stars. In the sun, it accounts for only about 1% of energy production. Recent experiments have finally confirmed direct evidence of CNO neutrinos, a triumph decades in the making. And so what if, just hypothetically, the relative contribution of reaction pathways fluctuated slightly? Historians still argue whether magnetic fields in the solar interior could subtly influence energy transport rates near the tachocline, the boundary between the radiative and convection zones. Some speculative models propose magnetically mediated mixing effects. Most remain unproven. You resist the urge to dramatize. The neutrino variation is small. It could be statistical. It probably is statistical, but it aligns temporally, loosely, with the surface magnetic irregularities and the contained flare. Correlation is not causation. Scientists repeat that like a lullaby. Still, patterns are curious creatures. You imagine the sun's core, 15 million degrees Celsius, protons colliding under immense pressure. Quantum tunneling allowing fusion to occur despite electrostatic repulsion. A balance maintained for 4.6 billion years. Stable, relentless, patient, and yet even stable systems exhibit microvariability. On Earth, nuclear reactors require careful control rods and coolant systems. The sun requires gravity. Gravity does not blink easily, but plasma is complex. Magnetic fields thread through layers. Waves propagate inward and outward. Energy transport is not a perfectly smooth conveyor belt. Historians still argue whether gravity waves, internal oscillations deep within the sun, play a measurable role in short-term energy redistribution. Detecting such waves directly has proven challenging. You sit in the underground detector chamber in your imagination, watching faint blue flashes blink in still water. Each flash a particle born in the core. Each particle a messenger that left the sun 8 minutes ago. And the count is slightly elevated, not alarmingly, just enough to make someone double-check. You feel that now familiar sensation. Not fear, not excitement, but attentive stillness. The sun's surface flickered, its magnetic fields kinked. A CME exhaled asymmetrically. Earth's magnetosphere flexed unexpectedly, and deep beneath kilometers of rock, neutrino detectors registered a whisper just above average. None of it screams, but all of it hums. The sun may not have released something explosive, it may have released something subtle, a shift in rhythm, and you, tiny and terrestrial, are listening to ghost particles in the dark, trying to decide whether the rhythm truly changed, or whether you're only just learning to hear it. You rise back toward the surface, leaving the ghostly neutrinos and their blue flashes behind, and return to something visually simpler: dark patches and bright wounds in the sun's outer atmosphere. Coronal holes sound ominous, but they aren't holes in the way your imagination might suggest. They're regions where the sun's magnetic field opens outward into space instead of looping back down to the surface. In extreme ultraviolet images, they appear as darker areas because they're cooler and less dense than surrounding regions. Mainstream fact: coronal holes are sources of high-speed solar wind streams, which can travel up to 800 kilometers per second, roughly twice the speed of the average solar wind. When these streams interact with slower solar wind ahead of them, they create co-rotating interaction regions that can trigger recurrent geomagnetic activity on Earth. Unlike flares and CMS, coronal holes are steady breathers. Predictable, rotational. They come back around every 27 days as the sun turns. You examine recent solar maps. A sizable coronal hole has opened in the southern hemisphere, its dark expanse stretching like spilled ink across the ultraviolet disk. That alone isn't unusual during an active phase of the solar cycle. But there's something else. Adjacent to the coronal hole, almost hugging its boundary, is a luminous region of enhanced emission. Not a flare, not a classic active region, just a persistently brighter patch in wavelengths associated with hotter plasma. It's the contrast that catches your attention. Dark openness beside concentrated brightness. Historians still argue whether the boundaries between coronal holes and active regions are sites of enhanced magnetic reconnection due to open and closed field line interactions. These boundary zones can be magnetically complex, like tectonic fault lines in plasma form. You zoom in. The coronal hole's open field lines allow plasma to stream freely outward. The neighboring bright region, however, is dominated by closed magnetic loops trapping hot plasma. Open versus closed, escape versus containment. And right along that boundary, subtle fluctuations ripple. You replay the timeline. The odd flare originated not far from this interface. The restrained CME followed. The radio oscillation whispered through. Now you see faint jets, tiny plasma outflows, erupting intermittently along the coronal hole boundary. These are known as coronal jets, most typically caused by small-scale magnetic reconnection between open and closed fields. They're common. They're usually harmless. But here's the interesting part. The frequency of these jets appears slightly elevated over a short interval following the main flare event. Not dramatically elevated, just noticeably. Historians still argue whether coronal jets significantly contribute to heating the corona and accelerating the solar wind. Some models suggest they're minor players. Others argue they're essential ingredients in the sun's energy budget. You imagine the boundary like a shoreline where two tides meet, one streaming outward into space, the other looping back to the surface. Friction builds, magnetic tension accumulates, small snaps occur. Now, here's a quirky tidbit. Early solar observers in the 20th century referred to certain coronal features as streamers and plumes because they resembled feathers or rays during total solar eclipses. Before space telescopes, eclipses were the only times humans could study the corona directly. Entire expeditions traveled across continents just to capture a few minutes of darkness. Imagine crossing oceans for a 3-minute glance. Today, satellites stare continuously. And what they're seeing now is subtle but persistent brightening at the edge of a coronal hole. The temperature in that luminous patch appears slightly elevated, measured through emission line ratios of highly ionized iron. Plasma at a few million degrees Kelvin. Normal for the corona, but the spatial distribution is slightly asymmetric. Historians still argue whether asymmetries in coronal heating reflect deep-seated dynamo variations or are simply emergent properties of chaotic magnetic interactions near the surface. You check the solar wind data again. A high-speed stream from the coronal hole begins reaching Earth days later. It's stronger than initial estimates, but not extreme. Combined with residual CME effects, it creates a modest geomagnetic enhancement. Auroras shimmer faintly at higher latitudes. Beautiful, unthreatening. But here's the pattern forming in your mind. The flare was unusual. The CME was restrained. The magnetic field remained kinked. Neutrinos whispered slightly above baseline. Now a coronal hole boundary grows restless, jets flickering, brightness shifting. Each phenomenon lives in a different layer of the sun's behavior. Surface magnetism, coronal dynamics, particle emission, interior fusion signatures. They don't normally synchronize in obvious ways, yet here they seem loosely braided. You hover over the luminous patch once more. Spectroscopic data suggest mild upflows, plasma rising at tens of kilometers per second. That's modest by solar standards, but the persistence is curious. Instead of one explosive event releasing tension, you're seeing a sequence of smaller adjustments across different solar layers. It's like the sun redistributed stress instead of discharging it all at once. Historians still argue whether large solar eruptions are preceded by measurable multi-layer coupling events. Subtle changes in coronal holes, oscillatory reconnection, and magnetic shear that collectively signal instability. Predictive space weather forecasting is still evolving, and that's the heart of it. You are still learning. The sun's surface looks serene from Earth, a glowing circle rising and setting with dependable rhythm. But beneath that familiar face lies a magnetized ocean, constantly negotiating tension. Sometimes it screams, sometimes it sighs, and sometimes, like now, it seems to do something in between. Brightening here, darkening there, releasing energy in fragments instead of fireworks. The luminous region near the coronal hole doesn't explode, it glows. Steady, almost watchful, and you feel that gentle tug of curiosity once more. Not because the sun is threatening you, but because it seems to be adjusting its balance in ways your models didn't quite predict. As if it released something small and kept something else in reserve. You sit now at the edge of explanation. On one side, clean equations, magnetohydrodynamic simulations, peer-reviewed journals with reassuringly small fonts. On the other, the wide, slightly untamed landscape of ideas that live just beyond consensus. The sun has twitched, not dramatically, but persistently enough that patterns are forming across layers. And when patterns form, theories bloom. Mainstream solar physics offers several grounded possibilities. First, nonlinear magnetic relaxation. In complex active regions, energy doesn't always release in one dramatic flare. Instead, it can cascade through a series of smaller reconnection events, like a tangled rope slowly loosening knot by knot. That would explain the double-pulsed flare, the restrained CME, and the elevated jet activity near the coronal hole boundary. Second, flux emergence variability. Magnetic flux tubes rising from the convection zone may fragment during ascent. If a large tube destabilizes but partially reconnects before full eruption, you'd see exactly what you observed, contained energy release with residual tension. Third, wave-driven modulation. Magnetohydrodynamic waves, alpha waves in particular, can transport energy along magnetic field lines. If wave interference patterns shifted temporarily, they could produce oscillatory signatures in both flare emissions and radio frequencies. These are respectable explanations. They sit comfortably inside the framework of established plasma physics. Historians still argue whether current solar dynamo simulations truly capture the chaotic turbulence of the convection zone, or whether computational limits smooth out critical instabilities that only appear in real stars. Modeling a star is, after all, slightly more complicated than modeling a teapot. You lean back, because outside the mainstream, the ideas get creative. There are fringe hypotheses suggesting that planetary alignments subtly influence solar magnetic behavior. Jupiter, with its enormous mass, does exert tidal forces on the sun, measurable but extremely small compared to internal forces. Most solar physicists consider planetary forcing negligible. Still, correlations between certain orbital configurations and solar cycle timing have been proposed. Evidence remains weak, But humans adore cosmic choreography. Then there's the idea of magnetic memory, a speculative concept proposing that long-lived magnetic structures deep within the sun may persist across multiple cycles, subtly influencing surface activity decades later. Some dynamo models hint at this possibility, but direct evidence is elusive. And yes, in quieter corners of the internet, you'll find whispers about exotic physics, dark matter interactions within the solar core, hypothetical particles altering fusion rates, even passing primordial black holes grazing the sun's interior. Let's gently tuck most of those into the bedtime story category. Mainstream measurements show no credible evidence that dark matter significantly affects solar fusion rates at observable levels. And if a primordial black hole passed through the sun, you'd see far more dramatic consequences than a slightly awkward flare. Still, it's fascinating that the sun, so familiar, so daily, can inspire both rigorous science and imaginative speculation. Here's a quirky historical tidbit. In the 19th century, before nuclear fusion was understood, scientists proposed that the sun shone by gravitational contraction, slowly shrinking and converting gravitational energy into heat. That model worked mathematically, but only allowed the sun to shine for about 20 million years. Geologists promptly objected because Earth's rocks were clearly older. It took the discovery of nuclear fusion in the 20th century to resolve the tension. The lesson? Even confident theories can evolve. Historians still argue whether early resistance to nuclear fusion as the sun's power source reflected insufficient particle physics knowledge or simple conceptual inertia. Scientific revolutions rarely arrive quietly. Now you return to the present anomaly, the subtle neutrino variation, the oscillatory flare, the restrained CME, the restless coronal boundary. One each can be explained individually within known physics. The real question is whether their coincidence implies coupling. Is the sun behaving like a system redistributing internal stress across multiple layers? Or are you, pattern-seeking human that you are, weaving threads that aren't truly connected? Cognitive bias is powerful. Apophenia, the tendency to perceive meaningful patterns in random data, has fooled better minds than yours. If you stare at solar noise long enough, you'll find shapes. Scientists guard against this with statistics, cross-validation, and replication. Independent observatories, independent teams, transparent error margins. So far, no alarm bells, just raised eyebrows. And perhaps that's the most scientifically honest place to stand. Not in fear, not in sensationalism, but in curiosity sharpened by restraint. And you imagine the sun as an orchestra. Most days it plays a familiar symphony, steady luminosity, predictable cycles, occasional crescendos of flares and CMEs. This week, a few instruments drifted slightly off tempo. The melody didn't collapse. The performance continued, but attentive listeners noticed. Historians still argue whether major scientific discoveries often begin not with dramatic anomalies, but with subtle discrepancies that persist just long enough to resist dismissal. The perihelion of Mercury, the ultraviolet catastrophe, the slight wobble in Uranus's orbit that hinted at Neptune. Small deviations can open large doors, or they can close quietly after recalibration. And that's where you are. The sun may have released nothing more than a routine adjustment, an ordinary redistribution of magnetic stress during an active cycle. Or it may have offered a faint preview of deeper dynamo variability that current models only partially capture. Either way, you're watching a living star refine your understanding in real time. No conspiracies, no hidden cosmic warnings, just physics unfolding across scales so vast that even a whisper carries weight. You breathe in that perspective. The sun shines on, warm and indifferent, and somewhere between established theory and imaginative speculation, you sit comfortably, aware that science thrives not on certainty, but on the gentle tension between what you know and what you're still learning to see. You let the theories settle like dust in sunlight. No rush now. The sun continues shining, indifferent to your debates and models and raised eyebrows. And you realize something quietly profound. Most of what you've witnessed isn't about catastrophe. It's about refinement. You sit beside climate scientists and solar physicists as they compare notes, Not dramatically, not with alarm, but with the calm intensity of people who've spent their lives studying a star that refuses to be simple. Mainstream fact: total solar irradiance. The amount of solar energy reaching Earth varies by only about 0.1% over the 11-year solar cycle. That's tiny, measurable, but small compared to the warming influence of greenhouse gases in recent decades. Solar variability contributes to climate patterns, yes, but it is not the dominant driver of modern climate change. That's important, because whenever the sun twitches, someone somewhere insists it explains everything. It doesn't, but it does matter. Subtle changes in ultraviolet radiation during active phases can alter stratospheric chemistry. Solar wind variations influence cosmic ray flux reaching Earth, which some researchers have hypothesized may affect cloud formation. The evidence for that link remains debated. Historians still argue whether correlations between solar minima, like the Maunder minimum in the 17th century, and cooler climate intervals such as the Little Ice Age represent strong causal relationships or complex overlaps with volcanic activity and ocean circulation shifts. The Maunder minimum, from about 1645 to 1715, saw dramatically reduced sunspot numbers. For decades, hardly any were observed. Europe experienced colder winters. Rivers froze. Paintings from the era show people skating on the Thames. But correlation is not certainty. Climate is a symphony of influences: solar output, volcanic aerosols, greenhouse gases, ocean currents. And your present anomaly? It's far smaller than a grand solar minimum. Still, the scientists run models. They feed in the slightly elevated ultraviolet emissions from the bright coronal region. They account for minor geomagnetic disturbances. They compare neutrino flux variations against baseline solar output. Nothing leaps off the screen, but small adjustments ripple through simulations like gentle breezes through tall grass. You imagine Earth from space, blue and white, wrapped in a magnetic cocoon. The sun's light arrives in 8 minutes, warming oceans, driving winds, feeding forests. Every meal you've ever eaten traces back to fusion in that distant core. And yet, for all that dependence, the relationship is remarkably stable. The sun has brightened gradually over billions of years as it fuses hydrogen into helium. Early in Earth's history, it was about 30% dimmer, a paradox known as the faint young sun problem. Historians still argue whether higher greenhouse gas concentrations alone resolved that paradox or whether additional warming mechanisms were involved. Stars evolve slowly, but magnetism evolves quickly. You think about the flare that didn't fully erupt, the CME that exhaled rather than exploded, the coronal hole boundary that shimmered with extra jets, the neutrino whisper that nudged upward. Perhaps the sun was simply redistributing magnetic stress across layers, preventing a larger release. Perhaps this is what stellar self-regulation looks like. You find comfort in that thought. The sun is not fragile. It has survived for 4.6 billion years through internal adjustments more dramatic than anything recorded in human history. And Earth has orbited steadily through solar maxima and minima, through storms and lulls. The data analysts lean back in their chairs. No emergency bulletins. No satellites tumbling from orbit. Just notes added to long-term records. Another data point in an ever-growing archive. You feel your breathing slow. The monitors glow softly. The magnetic maps continue updating in quiet loops. Somewhere underground, neutrino detectors blink blue in the dark. High above, satellites glide in predictable paths. The sun rises and sets as it always has. Historians still argue whether humanity's sense of cosmic vulnerability is amplified by technology. Ancient farmers depended on sunlight just as much as you do, but they did not worry about transformer saturation or GPS drift. Each era imagines its own fragility. You rest in the idea that vigilance is not fear, it is attention. The sun released something. Not a weapon, not a warning, a redistribution, a minor adjustment in the endless negotiation between gravity and magnetism. And you noticed, that is enough. Now the pacing slows. Imagine the surface again, not as a threat, but as a living ocean of light. Granules rise and fall in soft convection patterns. Magnetic loops arch and relax. The corona breathes outward in a constant solar wind that has washed over Earth since before life began. You are safe beneath your atmosphere, safe beneath your magnetic shield, safe beneath the steady warmth that grows forests and lights mornings. The anomaly fades into archived memory, not forgotten, just integrated. The sun hums. You hum with it. A star does not need to shout to be magnificent. Sometimes it whispers, and the whisper is simply part of the song. Let your thoughts drift now like plasma along gentle, magnetic lines. Let the questions soften at the edges. There will always be more data, more cycles, more careful watching. But for now, the sun shines steadily, and you can rest in that light. You don't leave the story when the sun settles. You follow the echo. Because even the softest solar adjustment travels outward, and Earth, wrapped in atmosphere and magnetism, always answers in subtle ways. High above you, in the ionosphere, sunlight is constantly reshaping the air. Ultraviolet radiation strips electrons from atoms. We're creating layers of charged particles that reflect and refract radio waves. It's why signals can skip across continents. It's why sometimes they fade without warning. Mainstream fact: the ionosphere is divided into layers, D, E, and F regions, whose density fluctuates with solar radiation, particularly extreme ultraviolet, EUV output. During solar flares, the D layer can intensify rapidly, absorbing high-frequency radio signals and causing shortwave radio blackouts. Your recent flare wasn't strong enough to cause widespread blackouts, but ionospheric monitoring stations did record slight, rapid increases in electron density, brief enhancements that aligned with the flare's double pulse. Not dramatic, but synchronized. Historians still argue whether small-scale ionospheric disturbances during moderate solar events are underreported because they fall below operational thresholds, even though they may reveal important coupling physics between solar radiation and atmospheric chemistry. You imagine standing at high latitude beneath a dark sky. Auroras ripple faintly above the horizon, soft green curtains trembling against black. These lights are born when charged particles from the solar wind spiral down Earth's magnetic field lines and collide with oxygen and nitrogen in the upper atmosphere. Oxygen glows green or red. Nitrogen blushes purple. It's atmospheric chemistry turned into theater. During the modest CME impact and high-speed stream arrival, auroral activity increased slightly. Not enough to trend on social media. Not enough for photographers to pack their bags at mid-latitudes. But magnetometers near the poles registered gentle pulsations. Geomagnetic pi, 2 waves, small oscillations triggered by magnetospheric adjustments. The Earth's magnetic field flexed, like a muscle stretching after a light tap. Here's a quirky tidbit. In 1972, during a period of strong solar activity, the U.S. Navy detonated sea mines off the coast of Vietnam months after they had been deployed. The cause? A powerful geomagnetic storm induced currents that triggered magnetic sensors in the mines. The sun, quite unintentionally, meddled in naval logistics. Space weather has a resume. This time, nothing detonated. But ionosondes, radar systems that probe ionospheric density, showed minor irregularities in F-layer height following the high-speed solar wind stream. So satellite drag in low Earth orbit increased slightly as the upper atmosphere heated and expanded. When solar activity rises, even modestly, the thermosphere warms. Increased atmospheric density means more drag on satellites. Most spacecraft compensate easily, but operators monitor these changes carefully, adjusting orbits when needed. Historians still argue whether cumulative drag effects during prolonged active cycles significantly shorten satellite lifespans in ways not fully accounted for in earlier mission designs. You float again above Earth's limb. The atmosphere is thin, just a fragile blue line against black space. Above it, the magnetosphere stretches outward, compressed on the day side by solar wind pressure, and trailing into a long magnetotail on the night side. During the recent event, instruments detected slight reconnection signatures in the magnetotail. Tiny bursts of energy release as Earth's magnetic field lines snapped and reconfigured under solar influence. Magnetic reconnection isn't exclusive to the Sun. It happens here too. The same physics, different scale. You realize something calming. The anomaly didn't just belong to the sun, it became part of a conversation. The sun adjusted, Earth responded. The magnetosphere flexed, the ionosphere shimmered, auroras whispered. No catastrophe, just interaction. Historians still argue whether Earth's magnetic field strength, currently slowly declining over centuries, could influence how future solar storms couple with the magnetosphere. The South Atlantic anomaly, a region of weaker magnetic shielding, already exposes satellites to higher radiation doses. But today's field is strong enough. Today's storm was mild enough. You feel the rhythm of it all. Energy leaves the sun. It crosses space in days. It touches Earth's magnetic boundary. It filters into upper air. It glows briefly in polar skies. And then it dissipates. The solar wind returns to baseline flow. The ionosphere smooths. The thermosphere cools. The auroras fade back into dark. It's easy to forget how dynamic the space around you is. You imagine space as empty, still. In truth, it's alive with plasma currents, charged particles, invisible fields linking star and planet in constant exchange. The sun doesn't just shine on Earth. It interacts with it, continuously. And this recent adjustment, subtle as it was, reminds you how sensitive that connection can be. Not fragile, responsive. Like two dancers lightly touching hands, each adjusting balance with the smallest shifts. You stand beneath the night sky now, real or imagined. Stars glitter quietly. The aurora has faded. The sun is on the other side of the planet, still glowing, still fusing hydrogen into helium with patient certainty. Its brief irregularities have passed into data logs. But the atmosphere remembers. The magnetosphere remembers. And somewhere in polar silence, instruments keep listening. Not because they expect disaster, but because even whispers from a star deserve attention. The Earth has answered, gently, and the dialogue continues. You return to the question that has been hovering quietly in the background the entire time. Was it real? Not the sun. The sun is very real. Bright, fusion-powered, gravitationally bossy. What you're questioning is the anomaly itself, a glitch or a warning. Will you sit again in the softly lit control room long after the flare curves have flattened and the solar wind graphs have returned to their steady hum? The excitement, if you can call mild scientific curiosity excitement, has faded into analysis mode. Mainstream fact, space-based instruments are constantly bombarded by cosmic rays, high-energy particles from outside the solar system. These particles can create false signals in detectors, especially in X-ray and particle counting instruments. Engineers design shielding and correction algorithms, but no system is perfect. So you start there. Instrument error, you cross-check timestamps. The double pulse flare appears in multiple independent X-ray detectors. The radio oscillation was picked up by ground-based arrays on different continents. The neutrino uptick sits within error margins, but across more than one detector cycle. A single instrument glitch is easy to dismiss. A synchronized multi-instrument artifact is much harder. Still, scientists are cautious creatures. Historians still argue whether some past anomalies in astrophysical data, once thought revolutionary, ultimately dissolved under improved calibration. Faster than light neutrinos in 2011 turned out to be a loose fiber optic cable. The universe was not, in fact, breaking Einstein. It was breaking a connection. You smile at that. Before rewriting physics, check your wiring. So you check the wiring. Telemetry logs show no temperature spikes in sensors, no radiation-induced resets, no software updates mid-event. The satellites were healthy, boringly healthy. You expand the dataset window. We'll look at weeks before and after the event. The sun shows typical active cycle variability. Flares rise and fall, sunspots rotate, coronal holes drift. Nothing leaps out as unprecedented, except that cluster, except that flare shape, except that whisper in radio frequencies. Individually ordinary, collectively unusual. You consider coincidence. In complex systems, independent small irregularities can cluster randomly, like flipping coins and getting 5 heads in a row. It feels meaningful, but probability allows it. Historians still argue whether human intuition systematically underestimates the likelihood of clustered random events, leading to overinterpretation in fields ranging from finance to astrophysics. You remind yourself stars are noisy, plasma is chaotic, magnetic reconnection is nonlinear. It would be stranger if the sun behaved perfectly smoothly. Then you examine predictive models. Before the event, space weather forecasts anticipated moderate flare probability from the active region. After the event, model outputs adjusted slightly, accounting for residual magnetic tension and coronal boundary changes. No model flagged imminent extreme eruption. No runaway cascade followed. If this were a warning, if the sun were winding up for something larger, you might expect escalating instability. Instead, the system stabilized. The magnetic field relaxed partially. The coronal jets subsided. Neutrino counts returned to baseline. The ionosphere smoothed. That leans toward glitch, or at least toward contained variability. But then there's the philosophical discomfort. Warnings don't always escalate immediately. Sometimes they're just signals, subtle hints that your models need refinement. Mainstream solar physics acknowledges that the dynamo process is chaotic. Small perturbations deep within the convection zone can propagate upward months later. The solar cycle itself varies in amplitude and duration from one iteration to the next. Historians still argue whether extended solar minima, like the Dalton minimum in the early 19th century, were predictable given prior cycle behavior, or whether they represent inherently unpredictable dynamo fluctuations. Prediction remains probabilistic. You zoom out further. Look not just at this active region, but at the global magnetic field. Synoptic maps show expected polarity patterns for this phase of the cycle. On the heliospheric current sheet, the vast wavy boundary separating magnetic polarities in the solar wind remains within anticipated tilt angles. Nothing screams structural upheaval. And yet, you replay the flare curve one more time. That hesitation, that second pulse. The sun doesn't owe you smoothness. Maybe this is what higher resolution observation reveals. Texture that always existed. Here's a quirky tidbit. When high-speed photography first captured hummingbird wings in motion, observers were shocked. The wings didn't flap in simple arcs. They rotated and twisted in complex figure-8 patterns. Reality was richer than the eye could see. Perhaps your instruments have simply become good enough to see the sun's hummingbird wings. Historians still argue whether scientific discoveries sometimes reflect technological thresholds rather than new phenomena, meaning the universe wasn't changing, only your perception of it. You let that thought settle. The anomaly might not be a glitch. It might not be a warning. It might be resolution, a finer lens revealing substructure in magnetic release events, coronal boundary interactions, and neutrino flux variability. You feel the tension ease slightly, because that possibility is not ominous. It's exciting. It means you are learning. The sun didn't unleash anything forbidden. It didn't hide something from you. It simply behaved in a way your models hadn't fully captured yet, and now they will adjust. Science does not require drama to advance. It requires discrepancies. Small ones are often best, so you lean back once more. Where the data has been archived, papers will be drafted, conferences will include one extra slide with a curious waveform and a cautious conclusion. Further study required. And the sun, it will rise tomorrow as if nothing happened. Because to a 4.6 billion-year-old star, your intrigue is the briefest flicker. The real question was never whether you were in danger. It was whether you were paying attention. And you were. You've circled the surface long enough. Now you descend again, past sunspots, past magnetic loops, past the shimmering corona, down into the engine room where gravity holds court. The solar core. Mainstream fact, the sun's core extends roughly 20 to 25% of the way from the center to the surface and reaches temperatures of about 15 million degrees Celsius. At pressures there are more than 250 billion times Earth's atmospheric pressure. Under those conditions, hydrogen nuclei overcome their natural repulsion and fuse into helium, releasing energy that powers everything you see. Fusion in the sun proceeds primarily through the proton-proton chain. Two protons fuse, forming deuterium, positrons, and neutrinos. Step by step, helium-4 emerges, and a small fraction of mass converts directly into energy. It's elegant, relentless, stable. The sun exists in hydrostatic equilibrium, gravity pulling inward, radiation pressure pushing outward. If fusion increases slightly, outward pressure rises. The core expands a little, and fusion slows. If fusion decreases, gravity compresses the core, heating it and restoring the reaction rate. It's self-regulating, like a thermostat powered by gravity. Historians still argue whether early 20th century physicists truly grasped how stable stellar fusion could be over billions of years, or whether the sheer timescales involved were psychologically difficult to accept. Humans are not naturally wired for billion-year patience. You imagine yourself shrinking, conceptually, diving through layers. First, the convection zone, where plasma rolls like a boiling ocean. Then the radiative zone, where photons scatter endlessly in slow diffusion outward. And finally, the core. No magnetic loops here dominating motion, no dramatic flares, just dense plasma under crushing weight. The neutrino whisper you noticed earlier, slightly elevated counts, would originate here if it were real. But here's the crucial thing. Even tiny variations in core temperature or density have feedback mechanisms. The sun doesn't allow runaway reactions the way fictional stars sometimes do in disaster movies. There is no sudden surge button. If the fusion rate increased by even 1%, the core would expand slightly, cooling itself and damping the reaction. Stability is baked into the equations. Still, physicists explore possibilities. One area of research involves gravity waves, internal oscillations deep within the sun, not to be confused with gravitational waves from colliding black holes. These internal gravity waves could transport angular momentum and subtly redistribute energy within the radiative zone. Historians still argue whether definitive detection of solar internal gravity modes, G modes, has been achieved. They are notoriously difficult to observe because their surface signatures are faint. If such waves shift patterns, could they modulate energy transport slightly? Possibly, but on timescales far longer than days or weeks. Then there's the tachocline, the thin boundary between the radiative zone and convection zone. It's a region of strong shear where rotation patterns change abruptly. Many solar dynamo models suggest this is where large-scale magnetic fields are amplified. If the tachocline's flow patterns fluctuate, magnetic flux emergence at the surface could change months later. That's a more plausible link to your anomaly. Surface irregularities might reflect subtle shifts in deep rotational dynamics. Here's a quirky tidbit. In the 1970s, some researchers speculated that variations in the gravitational constant, if it weren't truly constant, could affect stellar fusion rates. Precision experiments since then have placed extremely tight limits on such variation. Gravity appears reassuringly consistent. No cosmic dial twisting detected. You let that idea drift away. The sun's core is not a ticking bomb. It is a balanced furnace. But balanced systems can oscillate. Heliosysmology, the study of solar oscillations, has revealed that the sun rings like a bell. Acoustic waves bounce within it, creating measurable surface vibrations. These oscillations have allowed scientists to map internal density and rotation profiles with remarkable precision. Mainstream fact, heliosysmology has confirmed that the sun rotates differentially not only at the surface but also throughout much of its interior, with complex patterns varying by depth and latitude. And here's where subtlety returns. Recent heliosysmic inversions suggest minor temporal variations in rotational shear near the tachocline during active cycle phases. Small shifts, within expected ranges. But your anomaly occurred during a period of slightly accelerated surface activity. Historians still argue whether short-term fluctuations in internal rotational gradients can meaningfully influence magnetic flux emergence rates within a single solar rotation period. In simpler terms, can deep interior rhythms nudge surface magnetism faster than models predict? You don't know. No one fully does. That's the humbling part. Even with neutrino detectors and heliosysmic mapping in orbiting observatories, the core remains inferred, not seen. You sit at the center of your imagined descent. 15 million degrees. Fusion reactions flickering billions of times per second. Gravity holding everything in perfect, crushing balance. And you realize something calming. The anomaly you've traced, The flare, the CME, the coronal shifts does not require the core to misbehave. It doesn't require exotic particles or destabilized fusion chains. The sun's outer layers are dynamic enough on their own. The core continues its patient work, steady, measured, ancient. If anything changed there, you would expect signals far more dramatic than a subtle neutrino nudge. And yet the beauty of science lies in checking anyway, in asking the question, in listening for whispers even in the deepest furnace. You begin rising again, leaving the core behind. Gravity relaxes its conceptual grip. Magnetic fields resume dominance. And you carry with you a reassuring truth. The sun's heart is stable. Its surface may dance unpredictably. Or its magnetism may twist and hesitate. But at the center, fusion proceeds with calm inevitability. No hidden surge, no secret detonation, just hydrogen becoming helium, as it has for billions of years. The anomaly, whatever it was, belongs to the restless skin of the star. Not its steady heart. You don't stop at the core's reassurance. Instead, you listen. Because if the sun is a sphere of plasma under tension, then it doesn't just shine, it vibrates. Not audibly, at least not in the way your ears understand sound. Space is too thin for that. But inside the sun, pressure waves ripple constantly, bouncing between layers like echoes in a cathedral made of fire. Mainstream fact: heliosismology studies these oscillations by observing tiny periodic shifts in the sun's surface velocity, movements as small as a few meters per second. By analyzing these waves, scientists can infer the sun's internal structure, rotation rates, and density variations. The sun rings in thousands of modes simultaneously, a stellar chord. You imagine standing on the photosphere, again, hypothetically, because you would instantly become enthusiastic plasma, and feeling the surface gently rising and falling beneath you in patterns far too slow and subtle to notice directly. These oscillations are categorized into P modes, pressure modes, which dominate observations, and the elusive G modes, gravity modes, which probe deeper layers but are harder to detect. After the flare and magnetic irregularities, helioseismic data teams quietly check something specific. Did the oscillation spectrum shift? When large flares occur, they can sometimes excite localized seismic waves, nicknamed sunquakes. These are ripples that propagate across the solar surface following intense energy release. Your flare was not powerful enough to trigger a dramatic sunquake, but there was a faint localized enhancement in high-frequency P-mode power near the active region shortly after the double pulse. Not large, not globally disruptive, just a slight strengthening of certain oscillation amplitudes. Historians still argue whether small flares routinely excite detectable acoustic enhancements that go unnoticed due to averaging over the entire solar disk. Local effects can be diluted when you look at the whole star at once. You narrow the data to that region. There, a subtle increase in oscillatory velocity for several hours post-flare. It fades, but it's there. When you think back to the kinked magnetic field and the restrained CME, if magnetic energy was partially released but not fully, perhaps some fraction of that energy coupled into acoustic waves instead of erupting outward. Energy has to go somewhere. Here's a quirky historical tidbit. When scientists first began studying heliosismology in the 1960s and 70s, some skeptics doubted whether such tiny surface motions could reveal meaningful internal structure. Today, heliosismology has mapped differential rotation inside the sun with extraordinary precision. Sometimes the quietest signals carry the clearest maps. You let the data play out like music. Frequency peaks rise and fall. Mode splitting reveals internal rotation rates. The sun rotates faster at the equator than at the poles, a fact confirmed not just at the surface but through much of its interior. And during this active phase, rotation measurements near mid-latitudes show marginal acceleration compared to previous months, within expected variation, but trending upward. Historians still argue whether torsional oscillations, bands of slightly faster and slower rotation, migrating with the solar cycle, play a predictive role in surface magnetic activity. These bands drift toward the equator as cycles progress. The active region that produced your anomaly sits near one of these migrating bands. Coincidence? Likely. But patterns layer upon patterns. You imagine the sun as a vast drum. Magnetic fields tighten its surface. Flares strike it. Waves ripple outward and inward. Some waves dissipate in convection turbulence. Others reflect and interfere. The slight post-flare oscillation enhancement suggests that even a restrained magnetic release can tap into the sun's acoustic system. Not violently, just enough to be measurable. And here's something calming. The oscillation spectrum returns to baseline within a day. No sustained frequency shifts, no deep structural anomalies. If the core had destabilized, even slightly, you might expect broader, longer-lived seismic signatures. You see none. The star's rhythm remains intact. Still, the interplay fascinates you. Magnetic energy converts to kinetic motion. Kinetic motion feeds acoustic waves. Acoustic waves reveal internal structure. It's a closed feedback loop of information. Why historians still argue whether future high-resolution helioseismic missions could detect pre-flare seismic precursors, subtle changes in oscillation modes before magnetic eruptions occur. Predicting flares remains one of solar physics' great challenges. Imagine hearing the sun inhale before it shouts. Right now you're hearing it exhale, softly. The enhanced oscillations damp out as convection turbulence reasserts dominance. Granules churn, supergranules drift. The surface resumes its familiar shimmer. You rise higher, looking at the entire disk. Nothing outwardly dramatic remains, but you know that beneath the brightness, the sun hums constantly, a chord sustained for billions of years. And your anomaly, it added a faint overtone, a brief resonance. Not a cracked bell, not a broken string, just a momentary emphasis in the music. One you feel the reassurance in that, because a star that vibrates predictably, even when nudged, is a stable star. The sun sang a slightly unusual note. You recorded it, you analyzed it, and now the melody continues as before. No crescendo building ominously in the background. No deep tremor signaling collapse. Just oscillations settling back into harmony. You listen a little longer, then you let the chord carry you forward. You zoom out, farther than flares, farther than coronal holes, farther even than the 11-year solar cycle that has quietly framed so much of this story. Because the sun does not live on a single rhythm. It lives on cycles within cycles. Mainstream fact, beyond the familiar 11-year sunspot cycle, which is actually half of a 22-year magnetic polarity cycle, we researchers have identified longer-term variations in solar activity. These include the Gleisberg cycle, roughly 80 to 100 years in duration, and even longer periodicities inferred from isotope records in tree rings and ice cores. The sun breathes in decades, it exhales in centuries, and occasionally it seems to pause. You think about the Maunder minimum again, those decades in the 17th century when sunspots nearly vanished. Then the Dalton minimum in the early 1800s. Neither lasted forever. Both eventually gave way to renewed activity. Historians still argue whether grand solar minima follow identifiable precursors in preceding cycles or emerge chaotically from nonlinear dynamo interactions deep within the convection zone. In other words, can you see a long quiet coming, or does it simply arrive? The current solar cycle, cycle 25, has been slightly stronger than early predictions suggested. Sunspot counts have exceeded conservative forecasts, not dramatically, just confidently. Your anomaly occurred against that backdrop, a cycle gaining momentum, magnetic bands migrating equatorward, torsional oscillations subtly shifting internal rotation. Now you examine polar magnetic field strength. Polar fields near solar minimum are considered predictors of the next cycle's amplitude. Stronger polar fields often precede stronger subsequent cycles. Recent measurements show reasonably robust polar flux reversal underway. Nothing alarming, nothing collapsing, and yet, longer-term reconstructions using carbon-14 and beryllium-10 isotopes in natural archives reveal multi-century fluctuations in solar activity amplitude. Historians still argue whether these longer supercycles represent intrinsic dynamo modulation or are influenced by stochastic variability, essentially cosmic randomness amplified by nonlinear physics. You imagine the sun's dynamo as layered gears, Small gears spinning quickly, 11-year cycles. Larger gears turning slowly, century-scale modulations. Occasionally, the gears align in ways that amplify activity. Occasionally, they partially cancel. Your recent anomaly might be nothing more than a micro-expression of those shifting gears. A brief misalignment, a slight torque adjustment. Here's a quirky tidbit. In the early 20th century, some scientists speculated about a planetary clock regulating solar cycles, suggesting gravitational harmonics from giant planets impose long-term periodicity. Modern data show some intriguing correlations, but causation remains unproven, and internal dynamo chaos likely dominates. The sun, it seems, does not keep perfect time for anyone. You overlay decades of sunspot data in your mind, jagged peaks rising and falling like a heartbeat. Then overlay centuries, peaks waxing and waning in amplitude. Then millennia, long quiet stretches punctuated by energetic eras. Your anomaly is barely a pixel in that tapestry. And that realization is soothing, because perspective shrinks anxiety. The flare that hesitated, the CME that exhaled, the magnetic field that kinked but did not snap. These are not signs of collapse. They are expressions of dynamical complexity inside a star governed by chaotic plasma flow. Historians still argue whether deterministic chaos in the solar dynamo imposes a hard limit on long-term prediction accuracy. Beyond a certain horizon, precise forecasting may be fundamentally impossible, not due to lack of data, but due to the mathematics of nonlinear systems. The weather on Earth is like that. So is the weather on the sun. You imagine future scientists centuries from now reviewing archived data from your era. They'll see this event logged among thousands of others. Perhaps they'll smile at how carefully it was examined. Perhaps they'll use improved models to explain it easily. Or perhaps they'll note it as an early hint of a subtle cycle modulation that only became obvious decades later. Science is patient. Stars are more patient still. The sun continues rotating, about 27 days as seen from Earth, slightly faster at the equator, slower at higher latitudes. Magnetic bands drift. Cycle 25 will crest, then decline. Cycle 26 will rise. You feel the long arc of it. The anomaly wasn't an eruption. It wasn't a warning flare of doom. It was a reminder. The sun is not static. It is layered in time. Minutes of flares, days of rotation, years of cycles, centuries of modulation, millennia of grand minima and maxima. And beneath all of that, fusion ticking steadily for billions of years. When you zoom out far enough, the whisper becomes a brushstroke in a mural too vast to intimidate. The sun released something. Yes, a redistribution of magnetic stress, a slight acoustic resonance, a flicker in radio frequencies. But within the scale of supercycles, it was gentle. The gears did not grind. They shifted smoothly. You float in that perspective. On time's stretches, cycles turn. The star remains balanced between gravity and radiation, chaos and stability. And whatever small adjustment passed through its surface layers has already been absorbed into the larger rhythm. You breathe easier now, because the sun is not building toward a secret. It is simply cycling, as it always has. You've listened to the sun. Now you look at yourself. Because whatever the star chooses to do next, whisper, flare, or roar, your civilization will be here, wrapped in circuits and satellites, hoping the lights stay on. Mainstream fact: governments and space agencies actively monitor space weather. NOAA's Space Weather Prediction Center, NASA, ESA, and other agencies around the world track solar activity in real time, issuing forecasts and alerts much like terrestrial weather services. When there are scales for everything, solar flares are ranked from A to X class, geomagnetic storms from G1 to G5, solar radiation storms from S1 to S5. It sounds dramatic, like hurricane categories for a star. And in a way it is. You imagine a room filled with screens, solar imagery, magnetograms, particle flux graphs. Analysts rotate shifts 24/7. When a major flare erupts, alerts go out to satellite operators, power grid managers, airlines, and astronauts aboard the International Space Station. Astronauts in particular pay attention. During strong solar radiation storms, they may move to more shielded sections of the station to reduce exposure. Outside Earth's magnetosphere, say, on a future mission to Mars, the risk increases significantly. Historians still argue whether current shielding strategies for deep space missions are sufficient for extreme, Carrington-level events, especially during long-duration travel beyond Earth's magnetic protection. You picture future explorers, months from home, watching solar monitors as carefully as sailors once watched the horizon for storms. Back on Earth, power grid operators prepare differently. After the 1989 Quebec blackout, utilities began implementing mitigation strategies, installing monitoring systems for geomagnetically induced currents, improving transformer design, and developing response protocols. Modern transformers are still vulnerable to extreme events, but awareness has grown. SpaceX and other companies operating large satellite constellations have also learned lessons. In 2022, in a moderate geomagnetic storm, increased atmospheric drag enough to cause dozens of newly launched satellites to re-enter prematurely. Not catastrophic, but expensive. The sun doesn't need to destroy infrastructure to remind you it exists. Sometimes it just nudges it. Here's a quirky tidbit. During strong solar storms, some species of migratory animals, like birds and sea turtles, may experience temporary navigation disruptions because they rely partly on Earth's magnetic field for orientation. Imagine being a turtle calmly migrating and suddenly thinking, wait, was the ocean always slightly to the left? Even biology listens to the sun. You step back and consider preparedness. Space weather forecasting has improved significantly over the past few decades. As satellites positioned at the L1 Lagrange point, about 1.5 million kilometers from Earth, provide early warnings of incoming solar wind disturbances roughly 30 to 60 minutes before impact. Not much time, but enough to adjust grid loads or reorient spacecraft. Historians still argue whether investments in space weather resilience match the true statistical risk of extreme solar events. Carrington-level storms are rare, perhaps once every century or two, but their potential economic impact in today's interconnected world could be enormous. Risk lives in probability multiplied by consequence. Your recent anomaly did not test those systems. It barely brushed them. But it served as a quiet drill, an exercise in noticing. The flare that hesitated, the CME that exhaled, the ionosphere that shimmered. The satellites that logged mild particle increases. All of it moved through monitoring networks without triggering crisis. And that is reassuring. You are not helpless beneath the sun. You are attentive. Still, there's humility in the equation. Even the best forecast cannot predict every magnetic twist before it forms. Solar active regions can evolve rapidly. Magnetic shear can build in hours. Prediction windows are improving, but not perfect. You imagine the sun tomorrow, perhaps calm, perhaps more active, perhaps releasing another modest flare that fits neatly within expectations, or perhaps storing energy quietly for weeks before releasing it in a larger event. Preparation does not require fear. It requires awareness and adaptation. Earth has survived countless solar storms before humans ever strung copper wires across continents. Your species is uniquely vulnerable not because the sun has grown more violent, but because you've built delicate systems that depend on electromagnetic stability. And yet, you've also built systems to monitor and mitigate. It's a dance. The star moves, you respond. The anomaly you followed through this journey becomes something different now. Not a mystery, not a warning, but a reminder. You live under a dynamic star. You always have. The difference is that now you measure its pulses in real time. You log its whispers, you simulate its moods, you prepare for its storms, and most days it simply shines. The sun does not owe you stability, but physics grants you remarkable consistency. Gravity balances fusion, magnetism cycles, plasma flows, and when deviations occur, they ripple through a network of observers ready to interpret them. Sure, you feel a quiet confidence in that. Not arrogance, not certainty, just preparedness wrapped in perspective. The sun released something, you noticed, your systems handled it, and somewhere in a control room, someone wrote a small report that began with calm words. Event within expected parameters. Continued monitoring recommended, which in science is practically a lullaby. You return at last to the beginning, to the flicker in broad daylight. to the moment the sun seemed to blink. After all the layers, magnetic fields, coronal holes, neutrino whispers, seismic ripples, supercycles, satellites humming in orbit, you arrive back at something simple, a star adjusted, not catastrophically, not prophetically, just physically. Mainstream fact: the sun converts about 4 million tons of mass into energy every second, and yet its total brightness remains astonishingly stable across human timescales. Its variability is real, measurable, dynamic, but bounded by powerful, self-regulating forces rooted in gravity and plasma physics. That balance is the quiet hero of this entire story. The flare that rose in 2 steps, the CME that exhaled more than it roared, the magnetic kink that tightened and partially relaxed, the coronal boundary that shimmered, the neutrino count that nudged upward, the oscillations that briefly strengthened and settled. Each was a brushstroke in a living system constantly negotiating equilibrium. Historians still argue whether the most profound scientific realizations come not from singular dramatic discoveries, but from cumulative refinements, moments when subtle discrepancies sharpen understanding rather than overturn it. You feel that now. The sun did not release a secret weapon. It did not conceal forbidden physics. It revealed texture, the kind of texture that only becomes visible when your instruments grow sensitive enough, your models detailed enough, your patience long enough. You imagine the sun tomorrow morning. It rises over oceans and rooftops, over forests and deserts. Light spills across cities and mountains without hesitation. Solar panels hum gently. Leaves turn photons into sugar. Shadows stretch and retreat. No one notices that, weeks ago, a flare hesitated. No one feels the faint rearrangement of magnetic stress. And that's the beauty of it. Stars are allowed to be dynamic without being dangerous. Here's a quirky thought. If the sun were perfectly smooth and unchanging, solar physics would be far less interesting. No auroras, no sunspots, and no magnetic symphonies, just steady radiance, reliable but dull. The universe, it seems, prefers complexity over boredom. You stand again beneath the sky. It looks the same as it always has. But you know better, not because you fear it, but because you've listened more closely. Historians still argue whether humanity's greatest strength is not intelligence alone, but attention, the willingness to notice small deviations and ask careful questions about them. That's what happened here. You noticed a flicker. You traced it through layers of physics. You tested it against history. You examined instruments, questioned glitches, weighed warnings, and in the end, you found something both humbling and comforting. The sun is alive with motion, but anchored by balance. Its surface may twist and spark. Its magnetism may knot and unknot. Its cycles may wax and wane across decades and centuries, but its heart, its fusion-driven core, beats steadily beneath it all. If the sun blinks again, and it will, you'll be watching. Not anxiously, not dramatically, just attentively. Because that's the relationship you have with your star. It shines, you observe. It shifts, you learn. The flicker that started this journey becomes less a mystery and more a reminder that knowledge is not static. It refines, iteration by iteration, flare by flare. The sun released something you weren't supposed to notice, and you noticed anyway. Not because it was hidden, but because science has reached the point where even whispers leave footprints. Now the light softens in your mind. The magnetic loops unwind into gentle arcs. The corona fades into a quiet glow. The oscillations settle into a steady chord. Oh, the sun continues its ancient work. Hydrogen becoming helium. Gravity holding the line. Energy flowing outward across space. And you, small and thoughtful beneath it, can rest in the reassurance that nothing is unraveling. The star did not crack. It did not flare into fury. It simply reminded you that stability does not mean stillness. It means balance in motion. The sun blinks. You breathe. And the rhythm continues.